Complex circuits. We're going to start by talking about resistors in parallel. What happened when you put resistors in parallel in our lab after spring break? You might recall that they were all the same brightness as each other. That means that they had the same current. And because we assume they had the same resistance, that means they had the same voltage across them as well. Okay, so equivalent resistance for a parallel circuit. Here's the most simple parallel circuit we can have. Just two resistors in parallel with a battery. For each resistor, if there's a voltage across the battery, they each have that voltage drop across them. They each have resistance R, and we're going to assume that whatever current comes out of the battery is split in two between our two resistors. For the whole circuit, it has the voltage across the battery, the current through the battery, and some equivalent resistance that we don't know yet. Okay. So since both of those voltages for the resistor and then for the whole circuit are the same, I can set them equal to each other. Alright, so you see V equals I times the equivalent resistance. That's for the whole circuit. That's Ohm's law. And then also, if I apply Ohm's law to each resistor, I get 1/2 of the current across the battery times the resistance of each resistor. Well, since I have two things to equal each other, I can then solve for equivalent resistance in terms of the value of each resistor. Alright, my current drops out, and I don't have to worry about the V equals on the left, so I end up with my equivalent resistance is 1/2 R. Okay, but here's the for resistors in parallel. Here's our equation. Okay, now you'll notice on the left side of that equation it is 1 over the equivalent resistance. Okay, so once you add up the inverses of all the resistances, you have to remember to take the inverse again to get your actual equivalent resistance. That's the biggest mistake people make. Alright, and I promise this is the hardest equation for the whole unit. Alright, so here's a sample problem. For this circuit, where we have 3 resistors in parallel, what is the equivalent resistance if each resistor has resistance R? Okay, this is very similar to that first one that I did with just 2, except now I have 1 over R, plus 1 over R, plus 1 over R again, which is 3 times 1 over R. Alright, but I have to then flip it and take the inverse, so I get R divided by 3. Okay, complex circuits. That's what this whole lecture is about, right? Okay, so this is just a new vocab word, and it means when a circuit has some resistors in series and some in parallel. So I can't classify it as either a series circuit or a parallel circuit. This is probably the most simple complex circuit that you can make. It's got 2 resistors in parallel that are in series with another resistor. Okay, Kirchhoff's rules. Alright, you really actually know these in other terms, but we're going to define them here. Okay, he has 2. The first is the junction rule. You know it as conservation of charge. Right? My circuit is a closed system. So even if I come to a junction in my circuit where my current now has a choice of where to go, well, I can't create charge or lose it out of the circuit, so it must be conserved. And since current is charge per time, I can say that my current must also be conserved. So what this rule says is when the path of a circuit splits, the total current is still conserved. And you'll see this in an example in just a second. Okay, second rule, the loop rule. Alright, you know this as conductors want to be equipotential. You can also call this conservation of energy, because when we go around in the loop, I have to end up back where I started in terms of my energy. Okay, remember that electric potential was electric potential energy per unit charge. So voltage is very similar to energy. You can think in terms of energy. Okay, here they are in action. Here's the circuit. These aren't the values of the resistors, they're just numbered so I can refer to them. Okay, so the junction rule. I'm going to look at that junction, alright, where the circuit splits from one branch into 2, between resistor 1 and then resistors 2 and 3. Okay, I can say that the current through 1 is the same as the current through 2 plus the current through 3. Okay, that's a lot of words, so here's an equation. Alright, anytime you have a junction, you can say that all the currents going in must equal all the currents going out. Usually it will be a fairly simple case like this, at least in this class. Alright, the loop rule. Here's where it gets a little trickier. Alright, so we're going to look at the loop starting at that same junction. I'm going to go clockwise through resistor 2 and then back through resistor 3. The loop rule gets tricky because you have to keep up with the direction of the current. Alright, in both resistor 2 and resistor 3, the current is flowing to the right. Alright, from the positive terminal of the battery around to the negative terminal of the battery. Alright, so what the loop rule says is the potential drop across 2 is the same as the opposite of the potential drop over 3. Alright, it's a little bit hard. Alright, this all sounds super complicated, but I promise we can keep it simple. If you use Ohm's law, okay, say you're trying to figure out the equivalent resistance and then figure out the current through the battery. Okay, start with a simple portion and work your way out to the whole circuit. So here's a complicated circuit. Alright, the easiest part to start with is these two in series. I only say they're easier because you just add them up. They're in series. These two that are in parallel to each other are also not too bad to add up. Alright, so you can start with either of those in combination. Alright, once you have those two in parallel, you can add this one that they're in series with. So once I have those 3 in the middle, and the equivalent resistance of that whole branch, and I have the equivalent resistance of the 2 in series on the right, I now have 2 branches in parallel. Alright, the last thing we have to talk about is electrical power. Alright, light bulbs. When I go to the store, I don't buy a light bulb in amps, I buy it in watts. Okay, what were they a measure of? Power. And power is energy per time. Okay, here's the other equation that you should probably know from this unit. Electrical power, and again you can apply this to a circuit, a branch of a circuit, or any element in the circuit. It's simply the current times the voltage across that element. Okay? If I'm applying it to the battery, I take the current through the battery times the voltage of the battery. Okay, so one practice problem. What is the power dissipated in a 10 ohm resistor with 10 amps of current? Okay, the equation I want to use here is that power equals I squared R, because I don't have the voltage. So if I square my current, I get 100, and then my resistance is 10, so 100 times 10 is 1,000. Alright, here's some problem solving tips, just as a reminder. Okay.